This is weather over Arcata, California. Good flying weather for the landing aids experiment station hidden below. For here they stay on the ground when it is clear and fly when it's foggy, taking off, circling, letting down over the worst sort of country, and landing in weather that would close any conventional airfield. Some of the pilots who fly this weather as a matter of course are station pilots. Others are instrument-rated service pilots, assigned to Arcata for temporary additional duty to take part in tests designed to eliminate the dangers attendant on low-visibility landings. No, not an atom bomb. This mushroom is fog, lifted by heated air rising from the ground below. A landing is about to be made with the help of FIDO. Long lines of flares parallel the runway, heat the air so that ceiling and visibility in the runway area are brought above CAA minimums. A scheduled airline flight is able to land safely and on schedule at this, the foggiest airfield in the continental United States. The Landing Aids Experiment Station is situated on the coast of California near Humboldt Bay, 300 miles to the north of San Francisco. This former Naval Auxiliary Air Station was concerned mainly with FIDO development during the war. Today, it is an experiment and evaluation center for all landing aids. Under the operational control of a joint steering committee, the station is supported by the Navy, the Air Force, and the Civil Aeronautics Administration. Physically, it is run by a civilian airline contractor who operates the field. The contractor designs and fabricates mounts for installing equipment and systems to be tested. Supplies a staff of technicians to operate and service the complicated equipment necessary to the flight tests conducted in government-assigned aircraft by the contractor's staff of experienced pilots and by service pilots in service aircraft. The contractor also maintains an experienced aerology department for weather observation and analysis, skilled electronics personnel, able scientists, and research analysts, clerical personnel for the accurate keeping of records, and the publication of papers and pamphlets completely documenting the station's activities. Arcata was selected for landing aids work because it is one of the foggiest places in the continental United States. From July to December, warm, moist air from the Central Pacific is brought over a concentration of very cold water that wells up from the ocean depths adjacent to the coast in this area. The air is cooled by contact with this cold water, and heavy fog banks form just offshore. When airflow conditions are right, fog can move in and blanket the field in a matter of minutes. And night or day, when this happens, the station swings into action for flight tests. Nerve center of the tests is the control tower where supervisory personnel gather. Electronics men man the GCA. Observers go aboard. Experts come to Arcata from all over the world to observe these tests. Engines are started, and the flights commence. Test periods average about 2 hours in length if the fog stays in that long. Flights are touch and go. After taking off, each plane flies the field's traffic pattern, swinging out over the ocean and coming inland again southwest of the field. Approaching, it lets down toward the instrument runway. Observers see how the high-intensity lights stab out through the fog. There's a touchdown and then around again. Constantly flying the same sort of weather at this same field and using familiar landing aids have given these station pilots a better-than-average confidence and skill in low-visibility landings. And their confidence is backed by the perfect safety record of these tests. But the same methods are used to bring in all qualified pilots at Arcata, fast planes and slow ones, service planes and commercial, All are brought into a field that would normally be closed to air traffic, and it is done with an acceptable margin of safety. To carry on its work, the Arcata station uses landing aids which fall into three categories. First, electronic aids, which include ground control approach and instrument landing system. Second, high-intensity lights, both approach lights and runway lights. And finally, FIDO. To see how each is used at Arcata, we'll take them up one at a time. GCA, Ground Control Approach, is a war-borne landing aid that brought in thousands of service pilots safely and competently in bad weather areas all over the world. It is a system of landing planes by means of accurate verbal instructions from the ground to plane, transmitted over standard radio communication equipment and requiring no special gear in the plane. At Arcata, the GCA unit is located 390 feet west of the instrument runway center line and a little over halfway down its length. This is done for electrical reasons. Let's look at some of the operational aspects of the system. The GCA unit consists of three principal radars. One of these is a search radar. This traverses through the entire 360 degrees of azimuth. It picks up aircraft and terrain features in a 30-mile radius. The second, azimuth radar, covers only 20 degrees of the runway approach area. This radar makes it possible to determine an aircraft's position relative to the extended runway center line and its distance from the runway. The third radar shows the elevation of the approaching plane relative to the runway level and its distance from the runway. Here at pickup controller's position, airplanes in the vicinity are tracked visually on a plan position indicator, PPI scope. It takes a lot of training to be able to read and interpret a scope. For our purpose, a diagram will serve to show how the pickup controller directs traffic in the area and guides planes into a traffic pattern toward the instrument runway. Watching another PPI scope is the traffic controller. He transmits instructions to the pilot on his downwind and base legs. And when the plane has turned on final, he advises final controller by intercom. During this final approach, an azimuth tracker observes the airplane's position. This tracking provides information by which the final controller talks the plane in on final approach. The azimuth scope is an expanded position indicator. In magnified detail, it shows the airplane's position from the beginning of approach to touchdown. The scope is calibrated to show how far out the airplane is. Similarly, an elevation tracker observes the plane's elevation above the runway level, and by tracking, furnishes glide path information to the final controller. The elevation scope is scaled and calibrated to show elevation above runway level and distance away of the approaching plane. Through the adjustments made by the two trackers, deviations in azimuth and elevation are shown on scaled error meters. On the right-hand horizontal dial, the needle shows when the airplane is to the right or to the left of the extended runway center line. On the vertical dial, rising above or falling below the glide path is indicated by the moving needle. Using the error meter readings and distance information fed to him by the trackers, the final controller takes over voice communication as the airplane turns on final. From this point on, he talks the pilot in until visual contact and final touchdown have been made. At Arcata, special gear is used to study these approaches. This consists of recording apparatus in an adjacent trailer which keeps a complete record of each approach and landing, including both the voice communications and the airplane's actual flight path in elevation and azimuth. Flight path is charted on moving graph paper. GCA instructions are cut into acetate film and form a permanent record of the voice communications and talk down on each approach. To show operationally how the system works, let's follow through on a typical GCA low visibility approach. Here is the plane. And here is the weather at Arcata, where visibility is reported at 900 feet and ceiling 50 feet. Cleared by Arcata Tower for a GCA approach to Arcata, Air Force 637 is coming in from the north. His position, heading, and altitude are verified by pickup controller, who directs initial headings, informs the pilot of the field's elevation and prevailing surface winds, checks the pilot's name, the plane's type and approach speed, directs cockpit check, sets the altimeter and the communication wavelength. Yes, pickup controller carefully directs and follows the aircraft's approach. Once within a 7-mile range of the field, this direction is shifted to the traffic controller. This second controller directs the plane during the approach pattern, informs the pilot of the runway length and width, directs changes in altitude and heading to bring the plane straight towards the runway. With the aircraft 7 miles from the runway, direction is shifted to the final controller. Let's listen to the directions.
You are correcting the course. Present altitude is good. You are approaching a glide path. Begin your descent at 500 feet per minute. 125 feet below glide path. 100 feet below. 75 feet below. 50 feet below. 40, 30, 20, 10. On glide path. Adjust your rate of descent. Turn left, heading 310. Your new heading is 310. Going above glide path, 10 feet above. Ease it down a bit. Distance from touchdown, 4 miles. Turn left, heading 304. 30 feet above glide path. Bring it down just a little. Your new heading is 304. Turn left, heading 304. 30 feet above glide path. Bring it down just a little. Your new heading is 304. Coming down the glide path, 20, 10, on glide path. Turn right, heading 306. On glide path, your new heading is 306. Distance from touchdown, 3 miles. Wheels down and locked. You are cleared to land. Turn right, heading 308. Your new heading is 308. Going below glide path, 50 feet, 60 feet, bring it up. Still 60 feet below glide path, 50, bring it up. Turn right, heading 310. Your new heading is 310. You are coming up to glide path, 30 feet below, 20, 10, on glide path, on course, on glide path. Distance from touchdown, 2 miles. Turn right, heading 312. Your new heading is 312. Going above glide path, 10 feet, ease it down. Distance from touchdown, 1 mile. On glide path and holding nicely. Turn left, heading 310. Your new heading is 310. Distance from touchdown, 1/2 mile. On course, on glide path. Over end of runway, on glide path. Center line of runway is dead ahead. On glide path, on course. Over touchdown, take over visually. Contact Arcata Tower on 126.18 megacycles for taxi instructions. This is Arcata GCA, out.
Yes, routine stuff when you have the equipment and the experience. Smooth instrument flying and a pilot willing to take instructions, coupled with experience and knowledge in the GCA unit, spells success and safety. With ILS, the airplane's flight path on final is determined wholly by the pilot, who, flying on instruments, receives special guidance from the cross-needle ILS indicator located on the instrument panel alongside the regular flight group instruments. The ILS line in space is formed by the overlapping and intersection of radio fields transmitted from the ground and received by special gear in the plane. The localizer beam is the extended center line of the instrument runway. Its principle of operation is much the same as one leg of a radio range. Another beam sent out by the glide path transmitter establishes a glide path inclined gently upward from the touchdown point. The intersection of these two fields is the on-course, on-glide path line in space. Deviations in course or glide path introduce corresponding deviations in electrical field strength, causing the needles to deflect accordingly. At Arcata, the localizer beam transmitter is placed in a dugout on the ocean bluff at the far end of the instrument runway. Small directional antenna send a narrow on-course beam directly down the center of the runway. To guard against any wandering, the beam is checked by an operator at least once each day with an ILS-equipped Jeep. As it goes along the center line midway between the stripes, the beam registers on a single vertical needle instrument. As the Jeep driver turns off this center line, note how the needle moves to the left. Needle position is beam position. The circle in the center is the observer's position. Turning to the other side will move the needle to the right if the beam is functioning properly. As the Jeep returns to the center line, the needle moves back and holds steady in a vertical position, thus confirming accurate lineup of the localizer beam. The glide path beam is transmitted by another unit located 345 feet east of the runway center line and 1,180 feet in from the runway threshold. Directional antennas send out a beam sloping upward at a 3-degree angle to the runway. Set to give safe clearance over all obstruction in the approach path, this glide path angle is correct for any speed or type of aircraft. The aircraft itself requires a special design antenna to correctly receive the ILS signals, and a special radio set capable of receiving and translating the signals so as to move the needles on the ILS instrument. The vertical needle swings when the plane flies to the left of the course or to the right of the course. Thus, it indicates azimuth variations. The horizontal needle is activated similarly when the plane goes above or below glide path. When both are centered, the plane is flying on course down the sloping glide path. In this clear approach to the runway, compare visual position with the ILS indicator. Starting on course with crossed needles, we descend too slowly, and the dipping horizontal needle shows we are high. Now flying off to the left, the vertical needle swings right. To correct, pilot flies towards the needle. Overcorrecting, we swing to the far side of the on-course beam and then come back on course. We are still a little high. Note how the horizontal needle is just below the circle. It is easy to see how a good instrument pilot, keeping the needles nearly centered, can put himself into position to use the visual aids and so make a safe landing under any low visibility condition. Additional aids are needed to help the pilot get on the ILS beam and to tell him how far out he is from the runway threshold. There are two non-directional radio telephone beacon transmitters located at the outer and boundary marker sites. Using his radio compass and taking relative bearings on the outer station, the pilot can accurately turn on final. By later checking his bearings on the boundary station, he can check the accuracy of his approach to the runway threshold against his ILS indicator. There are also 3 fan marker beacon transmitters. Through radio receivers in the plane, these units flash a light on the plane dash. 4.5 miles out, the outer marker flashes 2 times per second. 3,500 feet out, the middle marker 6 times per second. And boundary marker 200 feet from the threshold sends out a steady fixed light signal. When fog covers the airfield, the pilot must get into correct geographic position for the ILS approach. To do this, he uses conventional instrument approach aids. Given weather information and clearance for an ILS approach by Arcata Tower, the pilot knows his letdown is subject to GCA monitoring as an added safeguard. He passes over the range station on his downwind leg and then turns baits. Taking up a heading of 040, he performs cockpit check. drops gear. He checks gear down and lock as he continues on base leg. Relative bearings are taken on the outer marker radio station. Note the ILS indicator needles off-center. On the last half of base leg, he swings gently left so that he can turn final without sharp correction. Careful coordination between radio compass indicator and ILS will put him into position for letdown. The radio compass shows the outer marker station ahead. ILS needles are crossed as we pass over the station. The radio compass bearing changes from directly ahead to directly behind. Marker light flashes 2 per second. Now squared away on final, we start our letdown into the overcast at 500 feet per minute. Crossed needles indicate we are on course. Now we are swinging off course to the right, and the needle swings left. Careful attention to the ILS indicator and smooth instrument flying are required for a good approach. On course, and we're headed directly for the boundary radio station. Going slightly above glide path, the horizontal needle is below the circle. Increasing rate of descent, the needle swings slowly upward. Middle marker, 6 flashes per second. The safety pilot picks up the approach lights and informs the pilot of their direction. The pilot switches from instrument to visual flight. Taking guidance from the pattern of lights ahead, he passes over the boundary marker, steady light, and levels off a little to the left of the center of the runway, but in safe position to settle into normal landing. Ahead is still plenty of runway so that he can bring his plane to an easy stop. As he chops inboard engines to taxi back to the line, GCA requests comments from him on the guidance received from various landing aids. The entire approach has been monitored and recorded by GCA, and on-the-spot comments are made while the memory is fresh concerning the approach. Had the pilot on the approach wandered far off course so as to put himself in a dangerous position, GCA would have warned him to pull up and go round again. And so another routine bad weather landing is completed, and more experience and evidence added to the book of bad weather flying knowledge being written by these people at Arcata.